In this video, in this study, we will talk about how power is estimated in digital circuit designs, especially from large designs where we specify the register transfer logic through Verilog programs or VHDL programs. Switching power, okay, that is the dynamic power that is associated with actual useful computation, the switching activity, is given by a factor alpha times F switching factor and C, the capacitance of the net, times VDD squared. So this is the switching power for one particular net. Say for example from this inverter gate here, that is the switching power on this net, where the capacitance here, C, is given by the total capacitance of the depletion of parasitic capacitance at the output node here, the wire capacitance, as well as the sum of all the capacitance to of the input gates that are connected to the wire. So this C here is the depletion capacitance at the output plus the total wire capacitance plus the sum of all input capacitances of every gate connected to that particular net. So in order to estimate switching power, we need to estimate these four factors: the switching activity and the toggle rate, the capacitance and the supply voltage of each and every gate output and input, and we sum them up, and that provides us an estimate of the total dynamic switching power, which is the power associated with useful computation. Now, the toggle rate is simply the average number of transitions, rise transitions as well as fall transitions of the circuit, and this is typically expressed as alpha and times some frequency, where frequency here is the clock frequency. So alpha is the switching activity. It is a static probability value that gives us the probability of individual nodes. What is the probability that the individual node stays at logic high? And FSW, this parameter here, is the clock frequency, and the combination of alpha FSW is the toggle rate, which gives us the number of rise and fall transitions, because power is consumed on every rise and every fall transition. So the toggle rates gives us the number of rise and fall transitions per unit time. To further reinforce the concept of toggle rate and switching activity, please look at these two curves here, which gives the switching activity, the time domain switching activity of pin CK and the time domain switching activity of a pin Q. Now if we take the total amount of time that the each of these wires, these nets, are at logic high, they are the same. Roughly 50% of the time the signal is actually at logic high, and 50% of the time the signal is at logic low. So the static probability alpha is the probability that the signal remains high, and in this case it is both 50% for CK and 50% for net Q. As we mentioned in the previous slide, the toggle rate is the number of up and down transitions per unit time. So if we just eyeball this, there are two up transitions and two down transitions here, but there are 4 up transitions and 4 down transitions here. So the toggle rate of pin CK is twice the toggle rate of pin Q, but their static probabilities are the same. Let's now consider this example here with pin CK here and pin Q here. In this case, there are, for the given computation duration, there are 2 up transitions, 2 down transitions, 2 up transitions, 2 down transitions. So the toggle rate for CQ and the toggle rate for CK and the toggle rate for Q are the same. That is, the same number of transitions per unit time. But CK has a probability, a static probability alpha of 0.5, because out of the total duration of time here, 50% of the time is spent in logic 1, and whereas in Q the probability is only 0.25, because out of the total duration of time under study, 25% of the time the signal is in logic high. So we are emphasizing alpha and the toggle rate, the static probability and the toggle rate, because we wish to get estimates of our circuit design switching power. So the capacitance can be extracted from the netlist. So that is the netlist after the place and route, because you would need to know the connections of each logic gate to every other logic gate. That means the output of the logic gate, which connections is made to the inputs of which logic gate. You need to know the type of logic gates being connected at the output, and as well as the logic gate itself that is under study. And you need to know the length or the capacitor parameters of the wire, and you need to know the size and the timing properties of individual logic gates. So these can be extracted from the post, place and route netlist. So the capacitance and the supply voltage is known if you have set the PVT, the process voltage and temperature corner at which the simulation is done, and you know the circuit. The supply voltage is known, but the switching activity and the toggle rate must be estimated, and this can be estimated from simulation files. That is, if you take the post, place and route netlist and you get the Verilog model of that, and you run it through standard Verilog simulators, we should be able to calculate the switching activity and the toggle rate. The toggle rate is important to give us the measure of dynamic probability, whereas the static probability tends to be more useful to estimate leakage power, because if your model specifies leakage power which is different at different input and output states, the static probability can be used to estimate leakage power more accurately. And one last thing to note, as you propagate logic through multiple layers of multiple stages of logic, we expect or we anticipate to see a decrease in toggle rate just because of the logic function. So here, for instance, the input CK has a toggle rate of 100 mega toggles per second, whereas CKE has a toggle rate of 200 kilo toggles per second. As a result of these two, the toggle rates at these two inputs, the output CKG of the AND gate is only 50 mega transitions per second. So as we progress deeper into more layers of logic, we do expect the toggle rate to progressively reduce. And of course, the toggle rate for D flip-flops can never exceed half of the toggle rate of the clock driving the D flip-flops. Let us now ask how we can obtain the toggle rate, the switching activity from simulation. So taking the post, place and route Verilog model, which is a Verilog netlist, and running the same simulation test bench or test setup on it, you can obtain the change in signal values for each and every net that or wire or register under consideration. And typically all these results are dumped, stored in a file called the .vcd file, where VCD stands for value change dump. And this table on the right shows the format of the VCD file. So typically the VCD file is an ASCII text file, and here the text file is broken up into two columns, but basically it's one continuous ASCII text file that goes like that. And I'd like to highlight a little bit the format of the .vcd file. The first part here is really the header information, talking about simulation date, the name of the module, etc. And the most important parameter to pay attention to is really the time scale. In this case, it's 100 picoseconds, because in the later part of the .vcd file, any transitions on individual nets are given in terms of the number of clock ticks. Let's say it's given by #1 or #5 or hash 10. So hash 1 means after 1 clock ticks, hash 5 means after 5 clock ticks, hash 10 means after 10 clock ticks. And 1 clock tick is actually equivalent to the value 100 picosecond specified in the time scale. So that part is important. The second part of the .vcd file, which is this section, defines the names and properties of all the logic nets under consideration in the simulation. The command typically starts with $var definition, followed by the type of the net, whether it's a Verilog register or a Verilog wire, followed by its initial value, followed by a symbol, in this case sharp $, percentage, followed by the actual file name, the actual net name in Verilog, and the end command. The reason there is a symbol file, a symbol per register, it's because the .vcd tries to save the information in a compressed format. It does not record the full name of the file, of the net, but rather uses a symbol to represent the net, typically a 1 byte symbol, ASCII symbol. If the net is actually an array that is a bus having more than one wire. So I'm sorry, this is not the initial value, this is actually the size of the net. Then this is recorded in the value here, the size of the net, and the name, actually you can also see the Verilog form that gives the enumeration of the array from 0 to 3. The final section of the .vcd file, the most interesting section, is the section after the $dump variables command. This is where the value of each and every net defined in this region is recorded. Only changes and the time at which those change occurs is recorded in a .vcd file. That means to say, if we have a long duration simulation and none of the nets in the design have any transitions, this whole dump var section will be empty. So the way that this is defined, it is defined as a value followed by the symbol. So this section here contains the initial values of the dump of all the variables. That is, so if you look for the hash symbol, the hash symbol is actually symbol clock. The initial value is 1. We look for the dollar symbol. The dollar symbol is actually the up down signal here, and the initial value is 0. We look for the exclamation symbol. The exclamation symbol is where is it? The exclamation symbol. So there's no exclamation symbol, so actually this file is incomplete. It's not defined in this variables section. So, but you get the idea. Now the .vcd file can be very large, because for very complex designs which are simulated with multiple modules and many tens or hundreds of thousands of nets or even millions of nets, the actual size of the .vcd file can be prohibitively large. And if one were to track analyze and count the number of transitions per net, it would take some time. So modern power analysis software tools also produce a more truncated file called the SIAF file, which stands for switching activity interchange format, And this SIAF file is generated from the .vcdd file from tools, but it gives a more summarized form of the activity. That is, you can find information that will let you derive the static probability activity directly and the toggle rate directly for each and every net. So the .SIAF file is an IEEE standard, specifically IEEE 1801, and this is the approximate format where the parameter of instance is here. You see the module name and then the submodule name. The timescale, that is the clock ticks, is given here. In this case is 1 nanosecond, and the total duration of the simulation is actually 8,630 nanoseconds here. And this is the name of individual nets or wires here being recorded. And here T0 refers to the total time duration when the net is at logic 0. T1, the time duration when the net is logic 1. And TC here refers to the total number of rise and fall transitions. So the static probability factor, alpha, is the total number of the probability of being at logic 1 is the total time in the circuits, the net spends at logic 1 over the total duration of the simulation, whereas the toggle rate, which is the number of up and down, rise and fall transitions, is given divided by the duration. So you will be able to extract one alpha and one toggle rate for each and every net. Here 3 nets are listed, that is clock, integer 6 and integer 8. Now the format of this SIAF file, which we just discussed, which was extracted from the .vct file by Power Analysis Software Tools, is known as the backward SIAF files. And this file is then analyzed by Power Analysis Tools to actually estimate the total number of the total power consumed, because the SIAF files, as has been discussed, gives both gives you the parameters to estimate the switching activity, the toggle rate of dynamic switching activity in all gates, in every gate. But you also have the possibility of specifying other SIAF files, that is called the forward SIAF files, that is input to the HDL simulator before the simulation is run. And the purpose of the forward SIAF files is to specify specific state-dependent conditions, that is specific paths which you would like to obtain toggle statistics and switching probability numbers. So for instance, if you were to just take the HDL simulator without any forward SIAF constraints, the simulator will generate backward SIAF files that gives you a per net statistics of the toggle rate and the probability rate, but you will not be able to derive the toggle rate with certain particular signal conditions. So if you would like to actually get additional statistics on certain particular state-dependent toggle rates, that is toggle rates when an input is in a particular value and output is in a particular value, or you would like to get the toggle rate along certain paths, that is consisting of multiple nets, you would have to specify a forward SIAF file. So an example of a forward SIAF file would have conditional statements like this, where here we are looking at the static probability T1, of course the probability of being at logic 0, and you could also get TC, the toggle count, and this would be evaluated in the case only when the net A and the net B is equals to 0. And when the net B is equals to 1 and the net A is equals to 0, there would be separate static probability and toggle counts that could be calculated. And of course, the default condition is just the conditions when all the other conditions that are not specified by the specific condition. And You could also specify in the forward SIAF file to only make toggle counts on only rise transitions or fall transitions on the signal, or to only count toggles along the entire path here consisting of ME and RW signals.